All right, 5.5 counting techniques. We're going to talk about different ways of counting using the fundamental counting rule, and we will also be talking about combinations and permutations. So the fundamental counting rule gives the total number of outcomes for events. It's where you multiply all of the possible things in a different event and you multiply them all together. You guys may have done this in middle school or elementary school when we talked about how many different outfits someone could have if they had 3 shirts and 2 pairs of pants and 2 pairs of shoes. And you multiply those together and you get a total number of outfits that could happen. So that's what the fundamental counting rule gives us. That's how we can find that. Here's an example. A coin is tossed and a die is rolled. Find the number of outcomes of the sequence of events. So you can make a tree diagram to do it, and then at the very bottom of that tree diagram, you count. And so then that would give you all of those. I don't do that. I prefer having an underline for each event. So this is going to be the coin, and this is going to be the die, and then I put how many different outcomes there could be from each of those events. So if a coin is tossed, that's 2 different outcomes. If a die is rolled, that's 6 different outcomes. I multiply those together, and I get a total of 12 different outcomes. Now, if you did that with a tree diagram, it would look something like heads, tails. We have that, and then you're counting all of these. How many different things are there down here? You count those all up and you get a total of 12. So 2 different ways of doing it. I like this method and I use it a lot. I'll use it for pretty much all of the stuff that we're doing today where I have those underlines to help me keep track of what I'm looking at. Another example, we have a paint manufacturer. We have a color, a type, a texture, and a use, and we want to know how many different types of paint could be made based on those things. So again, we have a color, we have a type, we have a texture, and we have a use. So there are 1, 2, 3, 4, 5, 6, 7 colors, there are 2 types, there are 3 textures, and there are 2 uses. So you multiply all of those together and you get a total of 84. So now we're going to have a list of things based off of IDs. So you have an ID number, I have an ID number. These are different setups for how you can create ID numbers and rules for them. So we have 4 spaces and we want to find out how many different IDs can be made. So we're going to have 4 lines for all of these because there's 4 numbers that are going to go into our ID. Our ID is going to look something like 0, 0, 0, 0. And so for each of these spaces here, I need an underline and I need to figure out how many possibilities I have. So it doesn't say anything about repetition. So if it doesn't say anything about repetition, I'm going to assume that repetition can be used. And so I have 1, 2, 3, 4, 5. So I have 5 numbers, 5 numbers, 5 numbers, and 5 numbers. So that is equal to 5 to the 4th power, which is 625. Next, same setup. I still have my 4-digit ID. So I still have 4 underlines. However, now I'm changing the number of possibilities going in. So instead of 5, I'm using 0 through 9. How many digits are there from 0 to 9? There are 10. Be careful. A lot of people just write 9. If you include 0, there are 10 numbers. So we have 10. That means 10 to the 4th power, which is 10,000. So look how much bigger our pool of IDs got simply by adding more numbers. Going from 5 to 10 raises that number substantially. All right, next, again, we're still using our same 4 digits. But now I get to use 0 through 9 and letters. So how many letters are there and how many numbers are there? Well, we start with 10 numbers and 26 letters, so that's 36. So that gives us 36 to the 4th power. Which again greatly increases the number of IDs we can make. First 2 spots are numbers, last 2 spots are letters. Again, start off with our 4 placeholders. Those 2 are numbers, those 2 are letters. (10 squared times 26 squared. $76,600. For this last one, we are now getting into the without replacement. So 1, 2, 3, 4. Now I have 10 numbers that I can pick here. But for the next one, I've already used one, so I no longer have 10. Now I only have 9, and then 8, and then 7. And so we do 10 times 9 times 8 times 7, and we get the answer of 5040. Notice, simply by going from with replacement to without replacement, we lose almost half of the available IDs. Next, we're going to get into permutations and combinations. For permutations, the thing that is very important is that order matters. Order matters. It's the first thing you should think of when you think of permutations. Order matters. The order in which you're putting something together matters if it's a permutation. Now, in order to be able to find permutations, we need to know what a factorial is. And a factorial uses this symbol here, which in computer science is called a bang. It's the exclamation mark. And what that factorial does, what that exclamation mark, what that bang does, is it tells you to multiply starting with the number you see all the way down to 1. So the example is 5 factorial is 5 times 4 times 3 times 2 times 1. So this tells you where to find that symbol in your calculator. 0 factorial is 1. That's a by definition thing, so be aware of that. 6 factorial. So 6 factorial is 6 times 5. Which is 720. Now another way of writing 6 factorial, and this is going to come in later when we start talking about permutations, is 6 factorial is 6 times 5 factorial. So the way to go from 5 factorial to 6 factorial is simply multiply your 5 factorial by 6, and then it becomes 6 factorial. And we're going to use that premise when we start talking about permutations. Suppose you need to rank 5 locations for a wedding reception. How many different ways can the 5 locations be ranked? So again, I like to go through, okay, well, we have 5 different locations and we're going to rank all 5 of them. Well, one of them can be the best place. So there's 5 different locations. Before I've picked one, all 5 have the chance to be best. Now, once I've picked the place that I like the most, there's only 4 places left for that next spot. And then so on, 3, 2, 1. And that becomes 5 factorial, which we already talked about is 120. So, in that case, if you're ranking all of the things that you have, it becomes a factorial. So I had 5 locations. I'm ranking all 5, so it's 5 factorial. If you're ranking 5 things, or you have 5 things and you're only ranking 3 of them, then it becomes a permutation. And a permutation uses this formula here. So NPR is the way it's written. You may see something like 10P2. So that is, you have 10 objects and you're taking them 2 at a time, and then the P says it's a permutation, so that means the order in which we're taking them matters. The formula for it is right here. Now again, I don't really use that formula. I'll show you the way I like to think about it. There's also a way of doing it on your calculator. So find 8P2 on your calculator. On your calculator, it will look like that. And you'll get 56. Now let's look at this using our formula here. So that n factorial divided by n minus r factorial. So n factorial over n minus r factorial. So that brings me to 8 factorial over 6 factorial. Now those are both fairly large numbers. They're not massive, but I don't know what 8 factorial is in my head, and I don't know what 8 factorial divided by 6 factorial is in my head. However, there's a way I can rewrite 8 factorial to make my life substantially easier. And that is, 8 factorial is the same as 8 times 7 times 6 times 5 times 4 all the way down, but I can stop at 6 factorial. And the reason I'm going to stop at 6 factorial is because then it allows me to cancel those 6 factorials out, and I'm left with a nice, neat, easy to find numerator of 8 times 7. And that's 56. And so because of the way that reduces, that's actually how I typically think of permutations. It allows me to make logical sense of what I'm doing and not just try and plug numbers into a formula and hope that the answer is right without knowing why. So I'll explain that again in this example. We have 5 wedding sites and we want to rank the top 3. So I'm going to rank 3 sites. So I put my 3 underlines. Now, how many different sites do I have for that first one? Well, just like before, it was 5, and then 4, and 3. But this time I stop. Again, if we did that using the actual formula, that's 5 factorial over 5 minus 3 factorial. 5 factorial over 2 factorial. Again, 5 factorial divided by 2 factorial reduces down to 5 times 4 times 3 times 2 factorial divided by 2 factorial, which is where I get my 5, 4, 3, which is 60. So anytime I'm doing these problems on my notes, on my tests, on quizzes, things like that, you will see that I will always be making those underlines to help me process what's happening. So we have 3 stories. We have a lead, a second, and a closing story, and we have 8 stories to pick from. So lead, second, closing, 8, 7, 6. And that brings me to 336. Next, a company is trying to pick a president, a vice president, a secretary, and a treasurer. So president, vice president, secretary, treasurer, from all 18 members. Well, that means I have 18, 17, 16, 15, and that gives me 73,400. So remember, in all of these situations, the order matters. I've named the stories: lead story, second story, closing story. I've named the positions that we're trying to pick: president, vice president, secretary. I'm ranking the sites, the top 3. So most favorite, second favorite, least favorite of those wedding sites. That's how you know if it's a permutation, is you've named the positions that things finish. The next one we're going to be doing is talking about combinations. And when we deal with combinations, the order of a combination, the order does not matter. And that's the difference between permutations and combinations. So the difference is, say, being on student council, you get voted to be like the president of the student council or student body. So you have president, student body, vice president, secretary. Those positions are named. So you have a position. You're the president or you are the vice president. Whereas if you have a committee and you get chosen to be on the committee, typically a committee isn't named. You're either on the committee or you're not on the committee. So those aren't named. That's a combination because it doesn't matter which position you're in. You're either on the committee or you're not. Toppings for pizza is a combination. It doesn't matter if you say pepperoni and sausage or sausage and pepperoni, you're going to get the same pizza. The order in which you put those toppings on doesn't matter. So in here we see an example of kind of how often or how that actually looks. So we have 4 letters, A, B, C, D, and then here is a list of the permutations. So you can see that AB and BA are both on it because AB is different than BA. Whereas for the combinations, you can see that we don't have that. AB and BA are the same, and so we only list it once. So what we've done to go from combinations to permutations is we've had to divide out all of those duplicates. And if you look at the formula here, this part of the formula is the same. So it starts the same. And then it adds that dividing by r factorial. This r factorial gets rid of all the duplicates. And so when I go through my process, I start my process the exact same way for combinations and permutations, but for a combination, I divide after I've done that because it starts off the same. We have the permutations. The next step is we then have to divide by this r factorial to get rid of the duplicates to make it a combination and not a permutation. Again, this shows you how to do that on your calculator, and on your calculator it would look like this: 8 NCR2. And then what your calculator is doing, 8 factorial, that becomes 8 factorial over 6 factorial times 2 factorial. Again, if we break that up into our pieces, we know that this piece is really 8 times 7. So that piece becomes 8 times 7, and then we divide by 2 factorial. The 2 factorial comes from how many things we're taking. So that's where we get that 2 factorial. The numerator is still the permutation calculation, but then we divide by the number of things we're taking at a time. And so that would be 28. Next, how many combinations of 4 objects are there? Taken 2 at a time. Again, this is 4 things, combination 2. I'm going to start off 4, then 3. This is what I would have if I had a permutation. However, now I'm going to divide that answer by 2 factorial. That gives me 12 divided by 2. And so the answer is 6. A mountain bike has 12 bikes in the showroom. The owner wishes to display 5 of them. So 1, 2, 3, 4, 5. And this would be 12C5. So 12, 11, 10, 9, 8. That would be my permutation. I'm now dividing by 5 factorial. It's 5 because that's the number of things I'm picking. And that's 792. TV station wishes to show 3 stories. There are 8 stories to pick from, so that's 8C3. This time it's a combination on a permutation because it's not naming the positions of the stories. It's not saying we're going to have a lead story, a second story, and a closing story. We just want to have 3 stories. And so again, we started off the same way, 8, 7, 6, but this time we divide by that 3 factorial. And we get 56. Again, for the last one, same concept. We're picking 5 people from 18, but again, because it's a committee and they're not named positions, I don't have a president or a vice president or any of that. It's just a group of people, a committee. That becomes 18C5, which again, 1, 2, 3, 4, 5. And that brings me a total of 8,568. All right, pause. Try and figure out whether these are combinations or permutations, and then come back afterwards and check to see if you got all of the correct answers. All right, so for the first one, locker combination, despite the fact that it has the word combination in there, it is a permutation because if you put your combination in incorrectly, in the wrong order, it doesn't open. If your combination is 1, 2, 3, and you put in 2, 3, 1, your locker won't open. The next 2 are kind of tricky. An ice cream cone with 3 flavors is a permutation because you have to eat them top down. If the top flavor is chocolate and the bottom flavor is strawberry, you can't eat the strawberry flavor first because the chocolate's on top of it. So you have to go for the top scoop and then the middle scoop and then the bottom scoop. You can't eat that bottom scoop first or the rest of the cone falls over. Whereas ice cream in a bowl is a combination because you can eat any of those 3 flavors because they're spread out. They're not sitting on top of each other. You can get access to any of the 3 flavors. If you're giving the same award to all 3 people that finish, that's a combination. If you're giving a different prize to the 3 finishers, that is a permutation. So chapter 5 is the first time you'll see this. It is no longer optional. It is just one of the 30, I think I said 35, one of the 35 homework assignments that you do that I drop. So again, I drop 1 homework assignment at the end, so it's really not optional. It's optional just like all of the other ones are. You get to drop your 5 lowest homework scores. Don't drop it. It's not new material. It is simply a combination of everything you've learned in chapter 5. All right, that is the end of chapter 5.